Okay, so for this question, I recorded everything, but the video was too long, and so now I'm having to do it all over again. So, my suggestion to you is first and foremost, draw this out and label everything. Alright, we're going to start off with our graphs, and initially we don't know what to put in for the graphs. We're going to calculate that. So we do our LOL graph, and we know that at the beginning we have potential energy, we have spring potential, and we have gravitational potential. So looking at our situation here, let's zoom in on what's important and what we need to calculate. So we're going to calculate the spring potential, 1/2 kx squared. We'll plug in our numbers, and I get my number. It's relatively small compared to the other energies. Now, we have two potential energies because we have two heights. So the first potential is for height 1, and the second potential is for height 2. Now, my graphs correspond with these 2 points, so there's the red dot and then there's the blue dot when it's at the top of H2. So for our graphs, for the red graph, it's going to involve both heights. Both height 1 and height 2. We're going to calculate them separately. It'll make sense later on. So we'll calculate the gravitational potential for height 2. That's mass times gravity times height 2. We get our answer for that. Now, the block starts off at rest, so it has initial velocity of 0, meaning it has no initial kinetic energy. So we have technically 3 different types of energy. So we have elastic potential, we have gravitational potential at height 1, gravitational potential at height 2. If I add those up, I'm going to get my total mechanical energy. So that's all the energy that we have to start with. And so when we draw our graph over here, we're going to label, I have elastic potential, I have 2 gravitational potentials, and those add up to a total mechanical energy of 165.89. Now, we have this little bit here in the middle, and so there's a rough section of track. That means that we have friction, and friction is going to take away some of our total mechanical energy. So on our graph up here, we have some work done by friction. To calculate that, it's not too complicated. We know the equation for work is force times distance. The force here is the force of friction, and that's the coefficient, mu, times mass times gravity. We're going to multiply by the distance, which is the length that they give us. So we're just going to multiply those 4 numbers together, and you're going to get some number for the work done by friction. This is going to be energy lost away from the system. So we're going to label that up here at the top. This is energy lost away from the system. Now, when we are at the blue point, when we're at the top of H2, this is our graph on the right-hand side in blue. There's no spring anymore, so no elastic potential. We do not have any gravitational potential. We've lost some gravitational potential. We still have some. We still have some gravitational potential. And that's equal to the gravitational potential at height 2. So that is still conserved. That's 78.4. We need to figure out how much kinetic energy we have. Before we can figure out the kinetic energy, we need to do this total energy. So the final total energy, that's equal to the initial total energy we had minus the energy we lost due to friction. Yeah. So that is our next calculation. We'll take our original total energy and subtract the work we just calculated. This tells us how much energy we have at the end. Well, we have at the final. And that is what we're going to use to find our final kinetic energy. So, the final kinetic energy and the gravitational potential, those must add up to this total mechanical energy. To find the final kinetic, we're going to take the total energy and we're going to subtract the potential energy we have at height 2. So my final kinetic energy comes out to be 66.48. And that is our small victory here. So everything else from here on, we're not going to use energy anymore. It becomes a horizontal projectile, and then we're going to go back to our projectile calculations, our projectile equations. So for a projectile, let's zoom there. The horizontal distance it goes, the equation we have for that is the horizontal velocity times time. Now, the reason why we had to find the kinetic energy was so we could figure out what that final velocity is. And to do that, we're going to just move around our kinetic energy equation. So square root of 2 times the final kinetic energy divided by the mass. Plug in our numbers. I get a horizontal velocity a little bit over 4. Remember, you have your own unique numbers, but your numbers should be similar in the same ballpark. All right, we're going to multiply velocity by time. So I need to figure out the time it takes for it to fall that height 2. Our time is square root of 2 times height 2 divided by gravity. So my height 2 is 1. We plug in our numbers, and I get a time less than 1. My time comes out to 0.4518 seconds. So now that I know the velocity, now that I know the time, we're going to multiply those together, and that will give me my predicted distance. How far away the block, or the object, the mass, is going to land. And my final answer comes out to be 1.842. So again, yours is not going to be exactly the same, but it should be similar, in the same ballpark. So it shouldn't be in the hundreds or in the thousands. And it shouldn't be less than 1. Less than 0. Okay, so there you go. And I'll just zoom out so you can see the big picture of everything that we did. There you go.